Ladies and gentlemen, we have been talking about waves and signals. It's just like saying one thing. Waves are signals, or signals are transmitted by waves. So today we are going to look at some properties of waves. As we said earlier, that waves are transmission of energy by oscillation, by the movement of back and forth movement of systems, whatever kind of system, and that way energy is propagated through a medium. In this case, we are going to consider, when we come to consider electromagnetic waves that can travel in empty space, we will treat empty space itself as a medium in which electromagnetic waves travel. But now we are still treating waves in their general form, and as we said, lest we forget that the purpose of these presentations are to debunk the hoax being propagated that the novel coronavirus disease is caused by 5G emission, which is actually not true. 5G emissions are electromagnetic waves. So we decided to treat waves in general before we come to electromagnetic waves, part of which are the frequencies that 5G networks use. So there are common properties of waves in general, both mechanical waves that travel in media like air, like water, like the earthquake, and also electromagnetic waves like light, radio transmission signals, radar equipment, and whatsoever you have. Signals are transmission of waves by back and forth motion of the sources or parts of the transmitting media. So we give examples. So properties of waves. Whenever energy is propagated in form of waves, it has certain predicates. Absence of these make something not a wave. So the wave is the substance, and these are what determines how strong or fast the waves are. We have, number one, amplitude. We have started talking about amplitude in the systems before, but we will expatiate about it. We do want to avoid mathematics completely, because this is a presentation for the general public. Wavelength. The wave has its own length. Then we have frequency. These are the things that we are going to discuss. Frequency, then speed. We also have a particular parameter we call the wave number. This is denoted by A in mechanical waves, but it may differ. This is called lambda, the Greek letter lambda. Frequency, let us put it as F. Sometimes it is given as nu. Then speed, we will call it C. For wave number, we call it denoted by K. So these are the fundamental properties of waves. We are going to also discuss the behaviors, because properties and behaviors in physical systems do differ. Behaviors: how does a wave move? How does a moving signal behave when it encounters an obstacle or when it passes through a certain opening, or when it is not hindered, or when it hits an obstacle coming back. All these, there are behaviors that depend on these properties of waves. As we said earlier, that amplitude, if we take the pendulum system, if this is the point of balance and we pull the ball here, this maximum displacement from the point of equilibrium is what we call the amplitude of the wave. Then, if it is unhindered without any resistance, when this comes back with a kinetic energy, it will still make the same distance of the amplitude A in this direction. Likewise, in your internal combustion engine, if a piston is attached to a spring and you compress the spring, the maximum compression you get is going to be the amplitude of the wave. So this, in simple, we say that amplitude of a wave is the maximum displacement of the wave from its equilibrium position. So if we are to plot a graph like this, say the distance along which the wave travels, and this, call this y, on xy, that is, this is xy plane. So if a wave is traveling in the xy plane, then let's say this, if it starts this way, for instance, if it is a spring like this, and you pull the spring upward, it has fixed endings, and you pull the spring upward to make it something like this. When you release it, maybe, or you pull part of it, sorry, maybe you pull a part of it. This is a fairly long string, so you pull this part of it to this point. When you release it, just like the pendulum will swing in the opposite direction, then this one will make the same distance by which you pull the spring upward here. Let us give a dashed symbol for the extension of the spring. Let's say this spring is extended to a height A, divided into the smaller heights. So the maximum height A here will be the amplitude. So on the XY axis, then it will be like this. So when you release it, after releasing this, the tension you applied will be transmitted in the other direction, this way. So, and just like the pendulum coming back to make another swing of our full amplitude, like this, as we say it, displacing it to an amplitude frequency. When you pull it to this direction, then if this is the negative direction, then here, then it will come back here. It will not stop at the equilibrium point. It will still make another amplitude A. So that way, the wave will continue to travel. So this is supposed in a free wave moving without damping. If a wave is undamped or driven with a constant force of constant frequency, it will continue in this way. We call it sinusoidal wave, because it is like a sine or cosine graph. So here you have the amplitude. This is the maximum displacement in the upward direction or in the y direction is the amplitude of the wave. Then number 2, we say wavelength. Wavelength is when a system makes a complete cycle. How does a system make a complete circle? For instance, if you have this, I will continue to use the pendulum example because it is the easiest to illustrate. So let's say this is in the negative direction minus a, this in the positive direction plus a. So when you pull it this way, makes plus a and comes back here, that is a complete circle. When it comes here, when you pull it here, you release it, it comes back and forth. When it comes to this negative a and come back to the positive a, it has made a complete cycle of motion. So on our graph here, the marks a complete wavelength, which makes a complete circuit. For instance, it's like this hyperbole in the negative direction and another parabole in the positive direction. So this is a closed path, but because it is dynamic, this one is not connected here. So instead of having this, you have it like this. Then the other one, because the wave is traveling, so this makes a wavelength. Now, frequency. Let us rush through the properties. Frequency. Wavelength is expressed in a unit called meter. That is the international standard of units. Then longer wavelength can be in kilometers, that is thousands of meters. But there are also smaller distances, that is like centimeter or 1/100th of a meter. You have a millimeter, 1/1000 a meter, micrometer, which is 1/1,000,000 of a meter. This is 10 to power minus 10. Okay, this is 10 to power minus 2. This is 10 to power minus 2. This is 10 to power minus 3, 10 to power minus 6, and so on and so forth. So even picometers, that is also the same unit in which amplitude is also expressed in meters, millimeters, centimeters, kilometers, and so on and so forth. You will come to say what is equivalent to an amplitude in electromagnetic waves. Amplitude in electromagnetic waves is the strength of the electric field, but we did not even talk about electric field. We will come to talk about it when we separate electromagnetic waves to discuss them as a special case. Then we talked of frequency. Frequency is the number of complete cycles, the number of wavelengths that a system completes in 1 second. For instance, let us use another system, the mass spring system, which we also illustrated. For instance, if you have a mass spring system, a mass arm suspended in a spring, and you pull it back to an extension E, the mass comes here. If you release it, it would come back to this point. Coming back to this point once makes a half wavelength. Then when it comes back, then it makes another half wavelength, half plus half, making one wavelength. So if it makes one complete cycle, or circle or whatever in 1 second, then it has a frequency of 1 hertz, named after Henry Hertz, a physicist who first detected electromagnetic waves. Then when it makes 2 complete cycles, for instance, if your pendulum makes two back and forth movements in 1 second, then it has 2 hertz. That means 2 circles in 1 second. When you are going to write hertz in full, you write it, you start with capital letters, hertz. But if you are going to make it a symbol, you use a capital H and a small z. So hertz also grow. Some systems make millions of cycles per second. Some make hundreds of cycles per second. Some make tens or dozens of cycles per second, depending on the driving force. It is only in quantum mechanics that we find that some frequencies are not dependent on the frequency of the oscillating system. But in classical mechanics, in classical physics, classical theory in general, the frequency of the oscillation, or the frequency of the waves produced, is equivalent to the frequency of the oscillation of the system. For instance, if you have electricity in alternating current or alternating voltage having 50 hertz, that voltage will be releasing radio waves of 50 hertz. This is to tell you that whenever we have supply from the national grid, Then our surrounding is